So what must happen for a reaction to occur? Well, reactants must collide. They must collide in the correct orientation, and they must collide with enough energy. Collision theory, really going back over this just briefly, is because in order to understand bond enthalpy, we kind of have to know the process going on in the reaction. So if they're colliding in the right orientation with enough energy, that initiates the bond breaking process. The reactants, the bonds have to break, and there's an energy amount for those bonds, and then they do their little intermediates, unstable, rearrangement going on, and then they end up reforming new bond, or forming new bonds, I guess I should say, forming new bonds in the products, and that's going to have its own energy amount. And here, that's what we're going to be looking at. So we're looking at the process of the bond breaking and the bond forming to be able to detect the energy change. So this is another way that they can have you calculate delta H of reaction, or the enthalpy change. One way was Hess's law. We've already done that, where we did the series of steps. That's one way you can calculate delta H reaction. Second way to calculate delta H reaction was through the heats of formation. Those are in the tables, in the textbook and the appendix, and online there's lots of heats of formation, and that's using the heats of formation equation, where it's like the moles times the heats of formation of the products minus the moles times the or the sum of the moles times the heats of formations of the reactants. And that's the one that's on the formula sheet, that particular heat of formation way of calculating the delta H reaction. Now what we're going to be doing here, this is going to be a third method of how to calculate delta H of reaction, and it's going to be based off of the bond enthalpies. So bonds have to break, bonds have to form. The energy change going on with the bond breaking, of course, in order to break the bond, you have to absorb energy, overcoming those forces. And that's always considered an endothermic process. And this is where we use that, easy phrase, AHxn is taxing, is to remember that. I mean, and maybe you can't visualize this because you've never had to chop wood with an axe or anything, but picking up an axe and chopping and splitting wood is a very, it takes a lot of energy to do that. You have to be pretty strong to swing that axe and break apart the wood. So that's kind of the analogy there, why AHxn is taxing, AHxn being the chopping part, and then which would be the bond breaking, and then the taxing part is here. It takes a lot of energy and makes you tired. So that's where that comes from. Of course, forming is warming. We've talked about this one before, forming the bonds, because the bonds forming is the exothermic process, and this is what's happening in the products. So energy is being released in that particular arrangement, so exothermic. So when a reaction occurs, you have both of these processes taking place. You have the bonds breaking in the reactants, you have the bonds forming in the products. Whichever value is higher is what's going to give the overall delta H of the reaction. So if the bonds that are being broken, that energy amount is higher than the bond energy that's being formed, your delta H is going to be positive, and so the overall reaction would be endothermic. The vice versa is true too. So if the bond energy in the products is higher than the bond energy of the reactants, now you're going to end up, when you do the calculation, with a negative delta H, which means the overall reaction is exothermic. So let's look at that equation. Delta H reaction is the sum of the bond energies that are being broken minus the sum of the bond energies being formed. All right, so using all of the words here, so BE, of course, representing bond energies of reactants, and of course the sigma symbol is the sum of the bond energy of the products there. What I have to tell you about this one, this formula is not on your formula sheet. You must memorize this one. Definitely take a moment to really get to know this one. The heats of formation one is on your formula sheet, but this one is not. And it's the reverse of all the ones that are on the formula sheets, because you have delta S, delta G, delta H. All of them are products minus reactants. And in this particular case, when we're talking about bond enthalpy and energies here, we are looking at really the ones that are breaking are the reactants, the ones that are forming are the products. So in this case, it's really the reactants minusing the products. And this is the only one where it's that sequence. All the other reactions, the entropy, the Gibbs free energy, the heats of formation, they all follow the same pattern of products minus reactants. This one in particular is the reverse, and the only one that's reversed, and it's not on your formula sheet, so you do have to memorize it. And they always ask a bond enthalpy equation for some reason. It seems like it pops up quite frequently on the AP exam. All right, so we're going to do a problem with this. Quite extensive problem, exercise 6. So here, for what the setup normally is for the problem is you're going to have an equation that's showing a reaction. In this particular case, this is a long equation because we have 3 reactants and we have 3 products. So this one's quite large. You're not usually going to have ones that are this large, but it is good for the exercise and for having an example to follow. The other thing they will give you is the list of the bond energies. Here's the bond, here's the amounts of energies, you know, the kilojoules per mole of the bond in there. And what you'll see here is this table of energies. Now, in the problem set, I'm not sure exactly how it's going to be set up, so I'm just going to go ahead and tell you. They may give you the chart like this, or they may like give you a link to a chart that's in the textbook, or a page to reference that has them on there that you look up the bond energies on there. Or, you know, I don't believe it's in Appendix 2, but they will reference a page in the textbook, give you a link, or give you the table. So you have those possibilities. Of course, you're never expected to have these things memorized. This type of data would have to be given to you. Now there isn't much space the way that's arranged, so I narrowed down the chart here so I have more space to write it out up here. But we're dealing with, you know, we're going to calculate delta H of reaction here, you know, doing the sum of the bond energies, you know, here broken, which is going to be the reactants, minus the sum of the bond energies, you know, formed. And so this we would really call like reactants. This we would really call products over here. Now, to determine the number of bonds and how much bond energy you need, you really need to know the structure of your chemicals up here. So I'm going to start the reactants, and I'm going to use a different color for reactants than I do for products, so I'll use green over here. Methane, CH4. If you can't look at that formula and be like, oh, that's 4 C to H bonds, then my suggestion is to you is to draw out a structural formula. A structural formula shows like the bond representation without adding all the lone pairs to finish off the Lewis dot structures. So for methane here, if I couldn't visualize how many bonds are in there, you could just draw it out real quick, do the little skeleton where you're just showing, oh, there's 4 single bonds between the C's and the H's here. So then I could note to myself, I have 4 C to H bonds here for this particular reactant. Then I look at my next reactant here, which is 2 chlorine molecules, elemental diatomic chlorine molecules. And C2, or Cl2, of course, obviously is a single bond between them. Once again, I don't necessarily need to draw out the entire Lewis dot structure and add all the lone pairs here, but another thing to remember is now that there's a 2 in front of this, that means there's 2 of them. So remembering that that's going to also play a role here in how you calculate and sum it up. So this would be 2 C to Cl bonds here for that one. Now this one, of course, fluorine, also diatomic, same idea as chlorine. The halogens are all single bonded. We know this. So that's going to be 2 fluorine bonds here, like so, as well. So we're going to add in the 2 F to F bonds here. This is all your reactant stuff. Okay, so got the reactants here, and this is going to subtract out. Here's our bond enthalpies of these guys. It's going to subtract out the products. So let's do the products. Let's try a different color for them. So here, CF2, Cl2, carbon's the central atom here. So this is going to be 2 of the CFs. Also forming a tetrahedral shape similar to our methane over there. And then the Cl's go in here. So we have 2 C to F's, as well as 2 of the, and this is like bracketed because, you know, this is a group together, this is a group together, like so. C, we have 2 of these as well, 2 of the C to Cl bonds, like so. And that's just out of that one particular product. Now we have 2 more products to deal with. So 2 HFs, that's going to be, HF is going to be a single bond, obviously. Pretty obvious, but there's 2 of them, so we have to note that. So 2 HFs, like so, and then the last product, 2 HCl's. So that's going to be 2 of them as well, and we would add that in, 2 HCl's. So these are our, you know, reactants over here. Here are our products. If you can't just mentally see and set this stuff up without, you know, drawing the skeleton structural formula, then draw it real quick so that you can count your bonds accurately, because if you don't count them accurately, you're obviously going to get the wrong number. So now we can plug and chug in here. I'm going to start with the bond form because I'm already in blue, so I'm going to start here with the subtraction part. So 2 C to F's. Well, C to F, I look at my chart as a bond energy of 485. So 2 of these 485s, multiply that, plus 2 of my C to Cl's, that's this 339, plus 2 of my HFs, that's 565. Wow, that's quite a large bond energy for a single bond. And then 2 HCl's here. So the H to Cl, that's down here at the bottom. So 427. So this is my products. Now I'm going to go back and do my reactants. So over here, I have 4 times my C to H, this 413. Plug in that number there. Oops, there we go. And then we have 2 of our Cl, this 239 here. And we have 2 of our F to F, which is this 154. So we have, yes, once again, our reactants and our products over here. And calculating our delta H reaction. Now we're going to use the calculator, of course, to come up with the overall energy. Yes, it is lengthy. This one is particularly large. That's a good point to make. Most of these problems have like 2 reactants and 1 product, or they'll have 2 reactants, 2 products. So you'll be able to do some cancellation and also, you know, bring it down a little bit. Usually they're not this lengthy. But I wanted to be able to show you, you know, a good one as an example to follow here. All right, so we calculate the reactants part, 4 times 413 plus 2 times 239 plus, oops, I forgot my little plus sign in there. That's not going to work. And now we have 2 times the 154. So this is going to be the reactant amount, which is 2,438. Oh, just to point out the kilojoule canceling, or the unit canceling, this is like 4 moles, and this is times kilojoules per mole. So that's why the moles get canceled out of the equation. So keep that in mind. It's similar to how we did the heats of formation one. Over here, 2 times 485. Now you're welcome to skip this stuff if you're really good with your calculator and can punch it all in at once. I'm just not that daring. I think I would mess it up. So I'm going to do the products and the reactants separate and then add it up. And once again, watching those signs, you want to make sure that you do that so that you don't mess up. If you get the wrong number at the end, then you don't get the point. So I'm getting, that doesn't look right. Actually, it is right. Okay, so I got 3,632 here for the products. That's the products, that's the reactants. So when you subtract these two, obviously we're going to end up with a negative delta H, which is negative 1194 kilojoules. So this overall reaction ends up being exothermic. Now you can just write kilojoules, or they like to see this too, where you put kilojoules per mole of reaction. Because we're not saying it's per mole of like individual stuff, we're talking per mole of reaction. So you definitely can do that there. And yeah, that would be the correct answer for this particular one. Once again, these problems are usually shorter. They usually don't have as many chemical species in the reaction. But do remember this equation, it's bonds broken, which are reactants, minusing bonds formed, which are products. So it's the opposite of what you would do for heats of formation. So the correct answer, yes, negative 1194 kilojoules per mole of reaction. All right, now we're going to talk about and analyze some of these bonds real quick and kind of review bond energy in terms of strength, length, atomic structure, and getting back into comparison, spiraling back to some of those concepts and what does it mean. Before we did kind of talk about bond energy and related it to bond order and things like that earlier, I believe back in Unit 2 or so. But numerically, the bond energy is a measure of the bond strength. All of these on this table, which applied to the last equation or the last reaction we just did with exercise 6, which one out of these happens to be the strongest bond? Which one is, yes, HF is our strongest because it's numerically has the highest value. So that's going to tell us that that is definitely the strongest out of all of these. And they're all single bonds here. And HF actually is quite a high value for a single bond energy. Usually they're not into the 500s. But say we're just comparing it to one of these other ones over here. What would you expect, say, a double bond in terms of its bond energy? Would it be higher than or lower than a single bond's energy? Yes, it typically would be higher because we know that bond order of 2 or double bonds have shorter length and are stronger because that's the normal trend. So if we were looking at bond energies for double bonds, you would see them in the 500 and 600 range. That's why I said this one's kind of an anomaly because it's typically single bonds are not that high. And we'll talk about why this one is pretty high in a minute. But what would you expect for triple bonds in terms of their bond energy? They're going to be the highest. And they're usually in the 900s, by the way. The triple bonds are usually in the 900s. So they're very, very high and are obviously very strong. So that's something to note. Now we're, comparing it in terms of bond length. Sometimes the bond length would be the reason. We're comparing their strengths, obviously, by their numerical values. But sometimes the reason is, talking about the atomic structure of the bond, okay? And remember here when we're talking about bonds, even the covalent ones where it's nonmetal like this, it's still a Coulombic attraction. It's not a lattice energy like the ionic. It's not metallic bonding with the sea of delocalized electrons or anything. But it's still a positive attracting a negative. You have your positive protons in the nuclei that are attracting the other element or the other atom's valence electrons. And there's attractive forces between those nuclei, but there's a little bit of repulsive forces also between the electrons. Don't forget that. And the overall attractive force is, calculated between those, the attraction for the protons minus the little bit of the repulsion of the electrons. So getting back to kind of recalling and looking at atomic structure from that standpoint too. Now we can look at and make some comparisons as to, analyzing these bond energies as to why they are what they are. So let's take a look at C to H, a carbon-hydrogen bond, and a C to F, carbon to fluorine bond. First thing we should do, of course, is look at their numerical values and decide which one is the stronger of the two. Which one is stronger of C to H and C to F? C to F is stronger, definitely. Definitely the stronger. Now, why? What can we come up with as a good reason as to why the C to F bond would be stronger? What is different about some of the arrangement here? Good point. Like that idea. Fluorine is the most electronegative element on the table. This is true. And it, electronegativity, remember, is a measure of the attractive force for electrons in a chemical bond. So fluorine has that very intense, high attractive force because it's a small element and it has a high number of protons for being such a small element. So that's why those electronegativity value for fluorine is so super high. When the electronegativity difference between the carbon and the fluorine, then, you don't really have to know the exact numbers, but relatively on the periodic table, the electronegativity difference of C to F is going to be greater than C to H. Like I said, you don't have to know this part because I know the values, I have them memorized, but the difference between C to F, the electronegativity difference, is 1.5. C to H is like about 0.4 here. So much larger electronegativity difference for C to F. Now C to H is still considered in the non-polar category of bonds. And of course this would be considered in the higher degree of polarity when we're talking electronegativity difference. Now, at first I was thinking also looking at the size of the atoms, although, hydrogen is one row above and has one less energy level, but because it's so far left on the table, actually, fluorine and hydrogen are actually quite similar in size. And I looked up the values earlier because I was questioning it during second. So hydrogen's measurable radius is actually a little bit smaller than fluorine, but fluorine's calculated one is smaller than hydrogen, so it's probably 6, to an even there. So on that one. So size isn't really all that notable here in terms of deciding whether the bond length is longer or shorter. But the electronegativity difference is huge. When you have a higher electronegativity difference, you have a larger dipole moment. You have a larger dipole moment, you have a stronger, you have a stronger force of attraction. Larger, polar bond. That's how I would look at these two and compare them. So the greater electronegativity difference between C to F here creates a larger dipole moment and a stronger polar bond with the higher bond energy. I guess I would also say in comparison to the C to H bond. You could probably also note in there, if you wanted to take a different route, say like the C to H bond is weaker because its electronegativity difference is smaller and it's more like a nonpolar equal sharing of electrons. That kind of deal. Definitely could go that route as well when trying to explain this. So that's one just comparison and analyzing, coming up with the reason as to why the bond energies are what they are. Now, they're not always going to be the same, considering which two separate bond energies that you're comparing. Now, of course, if you had like a double or triple bond in here, then of course you could cite the bond order, and that shortens the length and strengthens the bond and all of that as well, if you were comparing a single bond to a double bond or a double bond to a triple bond kind of thing. The next one is quite an interesting one. Fluorine bond or chlorine bond? So let's look here. We have our fluorine bond. We have our chlorine bond. Which one is stronger? Chlorine, which is kind of an anomaly because we know that fluorine is the most electronegative element on the table. So you would think its attractive force would be the strongest. So therefore, you would think that bond energy should be higher. I'm in complete agreement with that thought process. That's how I would have gone about it too. Now, can we think of a reason as to why the fluorine bond is weaker? It has less energy in it. It's easier to overcome and break that bond. Takes less energy to do so. Why would that be? Fluorine's smaller, the atoms are smaller, right? Because size-wise, fluorine has 2 energy levels and chlorine has 3. So the chlorine are longer, but longer doesn't go with stronger usually. That's weird, right? Doesn't make sense. Yeah, good point there. So what do we need to really start looking at? Let's think about, the size of the fluorines are smaller, but they have, 7 valence electrons each. So they're kind of cramming lots of electrons into a small space. Whereas like the chlorines are larger and they have more space and more, area to designate out their electrons. What do electrons do to other electrons? They repel them. So because of fluorine's very small size, with jamming all these electrons into that small space, the electron repulsions happen to be, quite a factor here. And because they have, more measurable electron repulsion in that small space, it's actually weakening the bond, making it easier to break. So this one is an anomaly, definitely doesn't follow any normal pattern, but if you think about it, that makes sense. I mean, it's all about the attractive force versus the repulsive force as to how strong the bond's going to be. And since fluorines are really small and have a lot of electrons to jam packed in that small area, the electron repulsions are pretty high there, I would suspect. And that's why we see the 154 in comparison to the 239. So although the bond length between would be shorter, we definitely would go with the idea that it's shorter because those are 2 smaller atoms. But the smaller size creates more repulsive forces between the valence electrons, weakening the bond and lowering the bond energy in comparison to the Cl-Cl. So definitely anomaly here. You wouldn't think off bat, but based off of the data, definitely shows that fluorine's weaker because the number's less. So we have to come up with the reason as to why it's weaker. It is smaller in comparison to chlorine that has 3 energy levels. However, the electron repulsions obviously create a problem here, weakening that bond, and that's why it has less energy needed to be absorbed to overcome it. All right. right, moving on to C. C to F, C to Cl here. C to Cl, C to F. Let's compare those. Why is CF stronger than C to Cl? I think there's a couple things we can note here. F is smaller, so the bond length is going to be shorter between the C and the F. And then the C to Cl, obviously, yes, fluorine has a higher electronegativity. It is going to create the more electronegative, or a huge electronegativity difference that's going to create the more polar bond. You do have a shorter bond length, and you have the electronegativity factor. So both of those together are creating the higher or stronger bond for CF and the higher bond energy number, numerical value. That would be the definite argument I would go to here when we're talking about this one. So CF has a higher bond energy due to the higher electronegativity difference, the larger dipole moment, and the smaller size creating a shorter bond length in comparison to the CCl. So I would note both in my answer, just because I'm strengthening my argument. But as you can see, the shorter bond, higher electronegativity difference with the larger dipole moment. You can succinctly say both in one sentence, because you know, talk long, talk wrong. You don't want to add too much, but you want to hit the keywords that they're looking for the point. And that would be what I would suggest for this particular type of question. So when comparing the differences, really what you're looking at is, because you both have carbons in each of the bonds, so it's really up to the fluorine and the chlorine being different here. And fluorine being the higher electronegative one is going to create a larger difference than chlorine, which it still has a pretty high one. It's like 3 or something, but it isn't as great as fluorine. So we know the electronegativity difference between the carbon and the fluorine is higher than the carbon and the chlorine. So good point. Yeah, we do need to pay attention to the difference, but in this case, they're giving us 2 atoms that are the same and then 2 atoms that are different in the bonds. So that makes it a little bit easier to compare. Last example here, looking at carbon with chlorine and hydrogen with chlorine. So let's investigate those numbers, look them up. All right, carbon with chlorine, hydrogen with chlorine. Which one's stronger here? And what would we say about it? On the HCl, definitely stronger. Now, what are some reasons that we can state for that? Shorter bond, I agree. Actually, the hydrogen is smaller than the carbon. I did look that one up to make sure. And you would think that way anyways, because hydrogen's just got 1 proton and 1 electron anyways. And yes, the electronegativity difference between the hydrogen and chlorine would be greater. Not by too much. I mean, hydrogen and carbon are kind of close, like carbon's 2.5, hydrogen's 2.1, so they're kind of close in their term of their electronegativities. However, it is still higher for the HCl in terms of the difference. So smaller size, shorter bond, higher electronegativity difference, that all I would say is easy to state here for this particular example. So although it has a slightly higher electronegativity difference, which creates a larger dipole moment, smaller size creates a shorter bond length and a higher bond energy and so forth. Yes, it is very similar to what you would say in the previous question. I agree with that as well.